So we will pick up from here. We have lost a lot of time, so let me see how much I can kind of make up. Okay. So as we showed the meaning of the expression, UI. Just a minute. The pencil is not writing. I'm not too sure, but okay. I think I need to put it down. Okay. I have to go back one more step, right? Now I think it will work. Okay. So I told you about the meaning of QI, UTFTI. It told you about the probability that if the system in the initial state was in the position against state QI, it has gone to QF. So probability that you have gone from QI to some QF at time TF. So it is given that you are at QI TI, the probability that it will go to up to TF is given by this matrix amplitude. And it can along which path it has gone, that we have not stated anything. But it may have gone through any path that is unimportant. So we have understood this is called the time evolution kernel. Remember, I told you about this time evolution kernel, and so now, so this is the time interval TF to TI. So time interval is now we divide the time interval to n equal intervals. Now this is very similar. This is very similar to our earlier picture. If you remember that I put n number of such hypothetical slits. So I consider that this entire time from the source to the screen, I break into some small pieces. So this is exactly I'm doing here. I'm just breaking the time interval into n equal pieces such that delta t equal to Tf minus Ti by n. And take in the limit. In the limit n goes to infinity, delta t goes to. So therefore, e to the power minus IH, if you remember, this was our term Tf minus Ti. All of you remember that I found U in this form. Here it is. Here you can see that I wrote this. So I am now taking that time evolution operator, and I write this as e to the power minus IH n times delta t. which is of course c to the power minus I h delta t times c to the power minus I h delta t dot e to the power minus I h. So what I have done, each of this is some that hypothetical, that screen that I put from the source to screen. I have broken the entire path into small n number of paths of small time interval delta t. So now what we do, I insert complete set of position eigenstates. You know that eigenstates of complete set of eigenstates of any Hermitian operator, position is a Hermitian operator for my basis, and their complete set. Complete set means normally if it's discrete, I said I summation over I equal to 1. For continuum, it is basically this is equal to the identity matrix. So I can assume that in each of these small time interval there is an identity matrix, and therefore here, everywhere. Therefore, I can write this. Therefore, UF UPFTI UI. I write this as DQ will be n minus 1 because n is the boundary, so DQ n minus 1 up to DQ1 times QF in the power minus IH delta t times Qn minus 1 is one complete set. So now you see that I have plugged in a number of such boundaries. So there are between 1 to I to F, if there are n divisions, I have broken into n part, there will be n minus 1 such small things, and I have just plugged into this. And I call this term QL e to the power minus IH delta t QL plus 1. That is probability that within this small time interval, if it was in the state QL, the probability that it will be in the position eigenstate QL plus 1. So this is called T L plus 1 comma L, or transfer matrix. So this is basically the probability amplitude of evolving from real to real plus 1. So now we have the expression for this thing, which tells us about this probability amplitude that we want to go from here to here probability. So remember that in Newton's law, we used to find that if the system is in Q at some point Qy at time Ti, then what will be its path? I mean, there is no question of probability. What is the path? where it will be at time tf. That was my question in Newton's law, where it will be at time tf. Whereas here I'm saying that it was in at position qi at time ti. What is the probability of finding this at qft? So the entire language of the subject has changed, but in the line of more mechanics rather than Schrodingerish approach, which is slightly odd in some sense. So in order to work it out, now assume a non-relativistic Hamiltonian H equals to p square by twice m plus p. So this is the, all of you know, that is the expression, very simple expression of time independent, non-relativistic. I'm playing for the moment you want with time independent. And also remember the identity that e to the power a plus b, if a and b are operators, then it is unlike e to the power a into e to the power b, that term is there, but there will be 1 minus half a commutator b, and then plus dot dot all the higher order commutators. So remember, if a and b are not operators, because ordinary C number, then the all commutators are 0. So it is just your old result e to the power a into e to the power b. But in general, if they are commutator, you cannot write it like this. Do you know why? Because their a plus b whole square is just not just e to the power a means 1 plus a plus a square by factorial to a 1 plus b square. These and a plus b whole square operators. So you know if there will be some kind of commutation thing will come because of the operator nature, they do not commute, and therefore you have to use this identity in order to calculate the when the operators are sitting at the top of the exponential. I hope you know this, but if you don't know this, then you can try it as an interesting homework. Now here a is p square by twice. So this is by a. So I identified this as by a, and b here take, and b as your, and p square by delta t, obviously, because you know that there is a delta t, and b is dq. Now AB, commutator AB has ordered delta t squared, because p square by twice m delta t, b is vq delta t. So if you take the multiplication AB minus ba, it will have a delta t squared, which we neglect in the limit delta t equals to 0. Because all of you know that we can neglect higher power of differential. Therefore, we find that e to the power minus I h delta t is equal to e to the power minus I delta t p square over twice m times e to the power minus I delta t v times q, and of course you have a 1 plus some commutators. You certainly have some 1 plus commutators, but which we neglect because the reason we have just mentioned, that they come with the quadratic of delta t. So we neglect that term for the time. So I find that this is simply e to the power. So okay. So the transfer matrix T Q L plus 1 comma Q, this becomes Q L plus 1 just e to the power minus I delta T P square by twice m times e to the power minus I delta T PQ, all are operators, times QL, because the commutator part is gone. So now what I do, I introduce a complete set of momentum basis. So if you do that, it becomes T QL plus 1 comma Q is equal to QL plus 1 e to the power minus I delta T P square by twice m. I introduce a complete set of momentum basis. So it becomes P of Q operator QL. But then, of course, you have to integrate over dp because you have introduced the complete set of momentum basis dp pp, which is equal to identity. So I've introduced an identity operator between this. So now we know pp is equal to pp and qq equals to qq. Again, state times this. So now you can immediately see that all the p square which will act on this p, whatever with the exponential power, it will just be p square times the eigenstate p, because the p square operator acting on its own eigenstate p. So p square, and so the p square that will now come out as an eigenvalue, those are not operators. So now what I get, so basically you get 1 minus p eigenvalue square. So now in the exponential power, what will become is just the eigenvalues p. Or similarly here, just the eigenvalues q, because q will act on q. So what I'm trying to tell you right now is that what I finally get is equal to, this is equal to dp e to the power dp e to the power e to the power minus I delta t p square over twice m e to the power minus I delta t pq, and you have ql plus 1 p, because these have, after operation they have come out, ql plus p, and of course you have a p acting on ql. Integration over dp I have already written, so it will no longer be there. So now try to understand, these are no longer operators. These are no longer operators, because after action on the state, they have become just eigenvalues, so no longer operators. So And so now what you do, so now you generalize this to the entire from QF to UTF TI. So earlier I one over a transfer matrix. So you just write all of them. So just like this, I have written one sample, so you just write all of them. And it is easy to show. It is very easy to show that what you get is absolutely trivial. It is equal to GQ n minus 1, GP n minus 1, I think I need to write one more step before I do this. Okay, please cancel this. I need to write one more step before I do this, so that you don't have any problem. I don't want to jump a step. So recall PQ was 1 by, this is the, you remember the position eigenstate in momentum representation was 1 by 2 pi to the power half. This was our normalization to the power minus I times. It is similar to the power minus kx minus omega t. So we write the momentum eigenfunction. So momentum eigenfunction is dual in the position space. You can all either way. So it's a momentum eigenfunction in position space if you take the dual. So you know this is the momentum eigenfunction. If you act with minus IH cross del Lx, you get the momentum. So this is the momentum eigenfunction in the coordinate representation, and you know that this is the so they always remember that PQ is QP star. So this is the, so QP is equal to power plus IPQ. So if QP star is equal to power minus IPQ. So this was the momentum. So I will just use this there to write one more step, that is equal to GP, because then it will be easier for you to write. You then just check that this is your term that will appear. Or minus I delta T H. It is there in any case, but now no longer operators. This is no longer operator, because this H is nothing but this H is nothing. So what I have done, I have written this quantity PQL and QLP. So so for one case I get this, and the other case I get this. So I get IP QL plus 1. Sorry, QL plus 1 and minus IP QL. So these two terms are here. This UL plus, sorry. So for one case, e to the power IPQL plus 1, and the other case e to the power minus IPQL. So I have written it, and e to the power minus II delta T. This H is no longer operator, but H is equal to E squared by twice M. So now you generalize this with this. So now you generalize this. For the full set QF, I did it for small infinitesimal path, but now I am doing for the full path. So the full path now looks from QI to QF is dq n minus 1, dp n minus 1 by 2 pi dot 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 2 dq1 dp1 for each of them. dq was already there. Now because of this transfer matrix I have a dp, so dp 2 pi. Remember I got a dp for each of this, and dq was there in my original q. Where is that? See here, I had so many dqs. So for every dq I have a dp also now, and this so this goes on, and finally what I get to the power I sigma delta t en qn plus 1 minus qn. You know that you have ql plus 1 minus ql time by divided by delta t. So I have what I've done. I had e to the power I pq, e to the power I pq, but I now have multiplied by delta t and divided by delta t. And of course, I had e to the power minus IH delta t, so I will have minus H sitting here. So what I've done for each of them, I have written that entire path for each of them, and I have this is the minus H delta t. So I have a summation for each of them. So from 1 to L, 2, 3, 4, 5, 6 are L, and then up to N, and then I have minus H which was sitting there. And I am writing this in the limit, write this in the limit n goes to infinity, delta t goes to 0. Now what was the picture? Picture was that you had a particle here at Ti, the position of the particle was Qi, and you are, so this is suppose you are sitting in your this room number 1, and in your house there is a room number 2, and you are going there. You are trying to find what is the probability. Firstly I wrote that this is equal to simply Qi UTF Ti QF, but now you find an amazing thing. You find that actually it is telling you that from this you first go to a path, infinitesimal path, say some q, so qi, so then you from there you go from 1 q small q1, then q2, then q3, and then up to finally after delta t such interval you reach here. Now this could be anything because you have integrated over all possible dqs, so it could be this also, it could be this also, because you have taken all possible initial and you have broken it into a number of pieces, but then you have integrated over all q's. So actually it tells you that you are passing through all the paths in order to go from qi to qf, and that is being shown here, what is written at the top. So now this picture, that it is very similar to the picture that I showed you during that electron diffraction experiment with putting some end, that actually you are going to the screen from all paths. So there is an empty space here, but when you are traveling through empty space, you are actually traveling from all possible allowed paths from here to here. So if you now write in a, so this I think can write that now in the limit n goes to infinity, qn plus 1 minus qn delta t, in the limit delta t goes to 0 because I am taking n goes to infinity. This is nothing but q dot, right? This is the derivative of q by definition. So what I finally have arrived at is that qf UTF TI QI is equal to integral. I'm writing in third bracket. I will explain this, what I mean by this. E to the power I. Now, what is at the top? This is P Q dot minus H. But you know that H is equal to P Q dot minus L. So P Q dot minus H is nothing but I L. And then, of course, you have summation over all such paths. So summation over the entire thing that you have in top. So this is nothing but is G where L equal to Pi Qi dot minus H. Therefore, this is nothing but the action. All of you know. I'm writing you what is dP third bracket and dQ third bracket. I will write it very soon for you. And this is e to the power is, and which is the function of P and Q. And what is dP? Let me write dP for you. This is product of all P's by 2 pi. And what is dQ? Is product of all Q's, because there were all dq product and all dq product. So I have written this in the following way. So this means I have this all these integrals. So there are so many integrals. You can see this, there are n number of degrees of freedom. So n plus n 2n integral is there, and S is of course action. S is action. S is function time Ti to Tf. So now you have a remarkable expression that U probability of going from some state Qi at time Ti to a state Q factor Tf is nothing but integral dP integral dQ e to the power is dQ. So this is the probability amplitude for transition from Qi to Qf. Yeah. So this is nothing but what is this? This is basically transition from Qi at Ti to Qf at Tf is equal to the right hand side. What is the right hand side? It is the sum of integrals over all or integrals over substance. Just a minute. Integrals over all phase space paths. Because phase space, because I'm integrated over both P and Q, as you can see. Qt Pt with boundary condition UTI equal to Qi QTF. Remember this integral when you are writing action, it is from Ti to TF. And you can see that here, this when you are, so you are allowed to take any Q and P's. You can see that when we are introducing this complete set, when you're introducing this complete set Q's and P's, so you are introduced complete set P's, it can be all possible P. And when you are introduced this complete set Q, where is that? Complete set here I introduce. Then use all possible Q's. So this QP they are completely unconstrained. Don't think that Q means Q dot is known, therefore P is don't know. They are total for any Q and P because I summed over all possible Q's and P's. Completely unconstrained and independent. So this is what is called Q and P independent totally. It's called Hamiltonian formulation. I am not taking Q and Q dot, but instead I am doing Q and P and summing over all possible Q's and P's. And therefore, as I said, the picture TQ, I am going from I to F, and it can go from any path like this, it can go to any path like this, so it's kind of going in its own thing. Hello? Okay, so now I can see that you can take any such paths to do this, and try to understand one important implication. The implication is that when you are going from here to here by this expression, summing over all paths, face-to-face paths are implied here. But each of them, for each of the path, you have a factor which is this. And therefore, remember that this factor is a kind of quantity, some modulator, which is associated with every path, because at every path of Q and P, every path for Q and P, where Q and P you are chosen some points in the face-to-face, this S can be calculated, and that quantity will kind of decide that as if some weight factor is coming with each path. So it tells you that among all paths, there is a factor which is this, which would kind of determine or modulate this probability transition. So this will be more clear when you do example, but I'm just trying to give you some understanding of the meaning of this entire expression. That while this Qy to Qf is given by this, I have shown that this is this can be written like this. So try to understand one important thing so far in this approach that Feynman has taken. The whole thing is determined as if you are going from one point to another. That is exactly what Newton was doing. But he did it that given a potential, the path is absolutely known. Here you are saying that given a potential, the paths can be different, but their weight factor for each path, of course, will change. And of course, with respect to specific problems, we'll understand the deeper meaning of it. But all paths in principle are allowed. So even a classical particle moving, all paths are allowed, that you see a definite particle when a bowler bowls a ball to the batsman. You see a definite trajectory of the ball. It is because this is that particular trajectory from that initial at the umpire end to the batsman end, QITI and QFTF. That particular trajectory will be appropriate weight factor, the corresponding action, that is the potential, plays an important role here to determine the corresponding probability. So this is the message. But see, this entire language, though we have gone from a deterministic to undeterministic picture, it is because of the uncertainty principle. But the thing is that this picture is so natural, and picture is so close to Newtonian mechanics. So Newtonian mechanics told you initial condition and he threw a law, and that law is ad hoc. Then you said, okay, I have an extremization principle. But extremization principle told you that there exists a unique path where it travels from this point to this point. The only new thing is that we are finding that no, in order to go to that, we can only talk of a probability, and probability of different paths are there, and which depends on the action S. And we have to calculate the full probability from QI to QF with the sum over all possible paths with appropriate weight. So that's the new picture. The new picture is so close to our Newtonian picture. And for this reason, I really like this, because this is a remarkable picture. I don't know, I have one more thing. So today we have lost some time. So let me see that how much I have covered here. Okay. So let me tell you the problem and I will tell this. Okay. So now I tell you about usable form or path. So one thing you can straight away say that, okay, I'll take all possible paths. I do this integral by putting the action. Yes, you can do it, but this is a very horrible looking thing. You can understand considering the entire thing that you are doing. So now I try to give it a little more. We try to make it a little more convenient. Sometimes you know that when we write something, it tells you everything, but it may not be very user friendly. So now we would like to make it a more user friendly kind of thing. So recall the transfer matrix. Because just, taking successive transfer matrix, you have to calculate the full probability. So by transfer matrix was T, QL plus 1, comma QL. So if we can do some simplification here, then I can do the simplification for the whole. And this was dp by 2 pi. And then I have e to the power I. Sorry. I over H cross QL minus QLP minus I delta T P square by twice M plus P. That was our expression for the transfer matrix, if you remember. And then we took remember, often you will see I am ready to use that. often you will see that people may not be using this H cross. They'll put this equal to 1 because we would like to work in a unit where H cross is Planck's constant is equal to 1. And remember this unit, which is called natural unit, you must have heard about it. See that in the thing, it's C equal to 1. C equal to 1 implies L equal to T. C is 1 means not magnitude 1 but also dimensionless. So L has to be equal to T. And H cross equal to 1. And Planck's constant is angular momentum, which is momentum into distance. So M velocity L by T into distance L. And this is dimensionless. L equal to T, we already know. So T is L, which implies ML equal to dimensionless. Because L equal to T means if put T equal to L, LL cancels. So ML dimensionless, which implies M equal to L inverse. So we work in an unit where mass is L inverse, L equal to T. And then in this unit, angular momentum is dimensionless. Angular momentum is dimensionless. Energy equal to mc square has dimension of m only. Any speed is dimensionless. So it's a funny unit. It's called natural.
Sir.
Yes.
Sir, there will be, I think, QL plus 1 in the exponential power.
Yes, sure. Of course. Yeah, thank you. Sure. Now, I will stop by making one. Then next day I will just handle this problem, and then we will see how beautifully you are solving problems. Integral I have written as one problem. Just realize this problem. This integral oscillates with P and Q and does not fall off, because you can see that there is an oscillatory factor e to the power I does not fall off as QP goes to infinity. So it's why this is a problem, because you know that if you integral some integrating over whole infinite space, you are integrating because you are saying I am considering all paths. So all paths means you going from I to F. You are going from I to F here. You are not only considering, you may consider a path which is coming to infinity and coming back to F. So it's going to infinity. So you're considering all paths. So remember this integral actually, but now earlier we had an advantage sometimes, except in a pure particularity box where there was normalization issue, that the wave function was oscillatory. But here you have a problem that this wave function, if it is falls off at large Q and P, then I can say this integral is doable because it's a square integrable because it is falling off at Q and P, but it is not doing it is basically oscillating. Okay. So we will a way to handle this. So how to handle this integral, because this integral is not really giving you some falling off. So which it's a kind of that when a summation is convergent, as you becoming larger and larger terms, then you can do the summation much easily than if it is non-convergent and oscillatory series, always problematic. So a way to handle this, so this summation integral is basically that. So way to handle this is to consider a complex version of this problem. With a small negative or positive, that's the negative imaginary part, epsilon, and eventually taking the limit So what I'm doing basically, I am now using a mathematical trick that I have a integral where I cannot solve. I am facing a problem in solving the integral. The integral is doing over infinite space, but it is oscillating. It is not following. So what I am doing, I am kind of making what is called, let me write, analytic continuation. You may have read it, but I will tell you what it is. Continuation to this problem to the complex plane. So what I do, the variable on which I was integrating, they were not complex. This, whether you take momentum or q, the q integral, because you know that you will have both q and p integral eventually, this dq and dp. So these are real quantities. So there is no question about it. So this is a real integral. But now I make an analytic continuation. Suppose I say for example, you have a variable x, which I am asking you to, you have an integrand, some function of x, and you are integrating and you are not being able to do it. I tell you, okay, fine. You take that x to be x plus some I epsilon. Epsilon is something like your imaginary part, y. And redefine that variable to be z. So now you have mapped the problem into complex plane. But you know that if the problem was real, I know that I said that yes, I know, but I could always remember that I am doing epsilon goes to 0 limit. So I am augmenting my real line integral into a complex plane integral. But eventually, when I take the epsilon goes to 0, actually I am falling back on the real plane. And sometime you will see what will happen, that this extension helps you to solve the issue very smoothly and very efficient, extremely efficient, and that would give you a beautiful picture of that when you solve something in the limit, solve. So you know that when solve something in the limit, say something like this, x square minus 4 by x minus 2. At x equal to 2, the value does not exist. But for the limit x goes to 2, it does. Limit x goes to 2, it is equal to 4. So what is the meaning of this? Meaning of this is that at exactly x equal to 2, it doesn't exist. That's true. But the function for arbitrary x close value to 2, and I argue that I am happy with that infinitesimal domain around 2. The value that in the limit that domain shrinks to 0, the value turns out to be 4. Here also, I am doing a real space integral, real line integral. I quickly jump to a complex plane, and I do the integral in a complex plane. So suppose this is now being a complex axis. So I do the integral like this, but you say that you are integrated from the x equal to some 0 to some x equal to infinity. But I say fine, but I made it pop up. But then I say this epsilon, the complex extension I take goes to 0, so it's almost just like this case. It is converging me to the real axis. So I get the result, which is very similar to the limiting case that you learned in calculus. So this is called analytic continuation. That is also this is also the you making a kind of function analytic in the sense that you are finding the limiting value of the function. So you are also finding the limiting value of the integral by extending it into complex plane and coming back to the real plane. So we will exactly do this, and we'll see that how much we gain by doing this, and we can handle the problem in a very simple way. And the problem of this oscillatory function can be resolved. And now we have a beautiful way to handle this. Now the question is, isn't this integral always doable. The expression that I have written is very, very compact looking expression, as you can see here. So, well, for putting some action, it may not be over all possible paths without BSc, but we will try to understand that when this can be done, there will be some specific cases where this can be done in a very reasonable way. Just as for Heisenberg approach to quantum mechanics, DDT of operator is I by H cross A, commutator H. For arbitrary problem, if I ask you to solve, it is not possible, it's not easy. So we go to Schrodinger approach and solve the usual differential equation. Here also it is similar, but we will show you that this method has some inbuilt advantage also. Though the problems we can solve usually by Schrodinger equation need not to be solved again always, but and some problems become very simple. But then there is some problem where this approach, as I said last time, this approach is a unique approach where you can solve this. But most importantly, I would say that this gives you a new picture of quantum mechanics. A picture in terms of paths in our real position momentum space in which Newton actually formulated his law. So you see the one interesting thing that I have noticed, that when Schrodinger did it, Newton did it, the law in a very ad hoc way. Lagrange approach gave it a more pictorial visualization by bringing in that approach. Here also, Schrodinger approach was pretty ad hoc. Heisenberg make it little more better than by saying that, see, this phi function has no meaning to us, but only because those are all constructed definition. But if you write Heisenberg equation, there is no psi. It is only in terms of dynamical variables, which actually is a mechanics approach. But even then, there were some kind of, strangeness, though it has some similarity to Poisson bracket, but that was not exactly Poisson bracket. All of you know that commutator bracket is slightly different, but it looks very similar to Poisson bracket equation. So Heisenberg did a great deal. But the Feynman approach to quantum mechanics, in a sense, is extremely, visualistic. He explained things just as some diagrams, some paths in our space, the way Newton taught us. But he did it in a way which is so convenient. May not be in terms of solving problems, but in terms of understanding I would kind of conclude by saying that we will make this integral, which is now a little bit messy looking, making it more user-friendly looking. And I wish that very soon you will learn quantum field theory when you'll see that the extreme power of this path integral approach to quantum mechanics. So now I open it for questions. So if you have any question, please ask.